Hello? Okay. This one works.
Okay, Andrea is our next speaker, and we'll talk about bootstrapping FluxTube.
Okay, thank you. And well, I will basically catch up from Sergey's talk, from the introduction, and we will switch to low energy. And I hope that after Victor's talk, everything will be clear. Okay. Okay. So this is working in collaboration with Joan, Aditya here, Joao, and Pedro. And so let's go straight to the point. And as Sergey was saying, we are imagining that we have like this long string. We are scattering excitations on top of this worksheet. We'll imagine that the target space is like d-dimensional. And we will work in units where the string length is equal to 1. So in d dimensions, you can imagine if you have this worksheet, there are d minus 2 Goldstone bosons, which are the transverse directions. So we have d minus 2 Goldstone bosons. And the scattering amplitudes, if you, as Victor will explain, can be parameterized in the following way. So we have, as usual, symmetric, antisymmetric, and singlet channel, as in Martin's talk, because of this OD minus 2 symmetry of the external particles. And the important thing that I want to stress about these phase shifts, from which you can read off the S matrix, or if you are more used to the S matrix, these phase shifts are related to the formula S is equal to 2I delta. Rep. The important thing is that these phase shifts are universal up to order S square. They're universal in the sense the slope is given by the scale that we set to 1. Alpha 2 is fixed to be some intriguing number, d minus 26 divided by 34 pi. And can be read off from an explicit one-loop computation. And there, because of the high degree of universality of this worksheet Lagrangian, the first non-universal correction arises at order S cube. So this one in yellows are these non-universal corrections. And in principle, they need to be fixed, matching your effective field theory with some physical data. So what I will try to do during this talk is to show how we can bound these coefficients. And in the case where the target space is 3-dimensional, we can do everything analytically. In 4 dimensions, we will need to rely on our Bootstrap numerics. But this is not the end of the story, because the bound of this on these non-universal coefficients, well, you know, it's not directly observable, the FluxTube S matrix, but what one can do, and people usually do, is to put it here in a cylinder and try to measure, for example, the energy levels on the lattice, like Sergey was doing for the glue balls. And for the ground state energy, I will show you that the bounds on these low energy constants translates into bounds into the ground state deviations of the ground state energy on a lattice. So to give you an idea, let me anticipate you the formula. So imagine that now you are wrapping this long string on a cylinder, and then some people measure for you the energies on the lattice. So this will be the radius R. And then, as again hopefully will be reviewed later, this ground state energy as a function of the radius, it will have like some universal piece, which is related to this degree of universality of the Brannon's phase shifts. And it's given by a famous square root formula, which is R squared minus pi over 3 d minus 2. And then, due to these non-universal corrections, there will be a shift arising at order R to the 7. And this shift will depend on the dimension. That after that will be some order 1 over R to the 9. And these shifts, depending on the dimensions, will depend linearly on these low energy constants. So let me give you explicit formula that I will comment later. Phi, then there is the dimension on D, and then there are the dimension these constants. Okay, so this is the introduction. And the logic, as I already told you, the logic of the talk will be, we bound these non-universal coefficients. We translate using the effective field theory, this bound on the energy levels. And then at the end of the talk, I will comment a bit about the resonances that can appear in the S matrices that we find on the boundary of the allowed region. Now, let me move to the setup. So, as usual, the setup that we use, like we assume crossing, unitarity. So let me list a little bit all the assumptions that we have. So first of all, since these particles are massless, they are two-dimensionals, they split naturally in left and right movers. And we assume that the only non-trivial scattering is between left and right movers. And the S matrix, let me write it again. It will be only a function of S because we are in two dimensions, so there is no angle, there is only the center of mass energy. And as a function of S, if A, B, C, D are the polarizations of these external Brannons, it will be given by three functions that, for example, as Martin said, that can be called annihilation, transmission, I will call it sigma 2, C delta BD, and reflection. And of course, when you use this notation, you need to fix a reference system for the polarizations. And well, I'm assuming that what I call S channel is this one, where I have A, B scattering to CD. Now, this is the ansatz. And then what about crossing? Crossing, since the particles are massless, is particularly simple. And basically states that the transmission amplitude is like invariant intercrossing. So sigma 2 in minus S will be sigma 2 of S. And that these two amplitudes, they switch under crossing. So sigma 3 of minus S will be sigma 1 of S. Now, why crossing is sense S to minus S? So I remind you that in 2 dimension, when the particles are massive, you have a threshold, the two-particle threshold for m squared, then you will have a cut at 0. And the crossing, it's just the fact that S, when it's sent to 4m squared minus S, which is T, the S metric has to be invariant. So of course, when you send the mass to 0, T it's just minus S, and the two cuts collide. But we keep this functional relation. And then there is unitarity. And then, as I just told you, the mass is 0, so the physical energy starts from 0. So unitarity will be the statement that the S matrix in the representations, and the representation will be just linear combination of the sigma 1, sigma 2, sigma 3 that Martin wrote on Monday, are just bounded by 1 for any S greater or equal than 0. This is unitarity. A last property that I need to use to justify what I'm going to do is real analyticity. So assuming real analyticity, which means that sigma I computed in S star, it's just sigma I star computed in S. Then I can relate, for example, the crossed channel amplitude to its conjugate on the other side of this cut. And then I can basically forget about the lower half plane and consider only the upper half plane, because it's related by crossing real analyticity to the lower half plane. So I will only consider this sigma as a function of the upper half plane. And that's it. So this is the setup. We'll consider a function that obeys these crossing functional equations, is bounded by 1, and it's real analytically on the upper half plane without the boundary. So, to start with, I promised you that when the target space is three-dimensional, we can do everything analytically. So let me just write here. So in 3 dimensions, there is something more that we can say about this effective field theory expansion, because particle production from the effective field theory, you can see that starts very late. Actually, it starts at order S to the 8, which means that the phases are real up to this order. So actually, in D equals 3, and in D equals 3 also, there is only one Goldstone. So these two basically do not exist. The only phase shifts is the singlet one. And then you see that in D equals 3, there is no S squared term. So there is no, this alpha 2, this term does not contribute. That is consistent also with the perturbation theory. And the non-universal correction starts at this order. So I will call in D equals 3 this coefficient gamma 3. And I'll call all the others gamma. So the phase shifts parameterization compatible with an effective field theory expansion. It will be given by S to the 4 plus gamma 3 S cubed, and then there will be eventually other coefficients that are all non-universal. But the important thing is that particle production starts at this order here. This low energy expansion is the one compatible with the effective field theory. Now, a trivial bound on this phase.
That doesn't look particularly real analytic.
Sorry?
That doesn't look particularly real analytic to me. Isn't high. Should you get a log or something? Like something really bad?
Yeah. Yeah. So this I, in a sense, comes from, you should get like a log of minus S, for example. So this I comes from this log. So I'm ignoring the logs that appear later. So eventually there will be logs. Yeah.
I think you said it's real analytic, right? And you should write something with a real series, two coefficients.
So more than a log, that seems like a square root of minus S. Sorry, or
No, the problem with the calculus goes away to 0. As you said, if you start with the massive theory, it would be real, and the fact all space equals 0, there is no cut, and then multiplication will be 0. And then you can consider massless limit.
I think it's okay to write something with a branch cut, but I don't think it's okay to write something that's analytic with complex coefficients.
I think the point is that once the cut is closed, you really have two functions, one above plane and one below.
Right.
And the only thing you know of the function above on the upper half plane is this combination of real and artistic with crossing that stays in the upper half plane. And that symmetry is important. If you combine.
Yeah, if you combine, yeah, you're right. Yeah. Yeah, sorry. Yeah, it was the, right. Yeah, in this order, they combine and cancel. Yeah, it's true. Thanks, I forgot this point. Okay. And this is basically the reason why you can forget about the lower half plane. And the analytic continuation has to be done taking your function and basically taking the conjugate and minus.
Purely imaginary S, in particular, here it should be real.
Exactly. So another way to see it is that when you go for purely imaginary I, since you have like, here you have your S matrix. Here, because of this relation, you would have your S matrix, S star. And then, well, because of Schwarz's principle, basically here on this line, it has to be real. So in particular, it's real on this line. That's another way to say it. Okay, thanks. So, but okay, so let's start again from this gamma 8. So I was saying like some trivial bounds on these coefficients are the unitarity bounds, because this when gamma is, well, when the power is even, basically, this gamma have to be all positive. Gamma 2n has to be have to be all positive because the functions, well, cannot explode. It has to be bounded by 1. But on the other coefficients, in principle, they are all phases because 2 delta S multiplied by I, so in principle, they are not bounded. So how is possible that we get some bounds? So to explain this, let me make a step back a little bit. Yeah. Right. This is this. And well, let's look. So let's imagine that instead of fixing, well, we have S to the 4 that we said it's the scale, but imagine that the coefficient is like some gamma 1, so that the phase shift start with gamma 1 S plus dot dot dot. Then we are saying that our function is basically bounded by 1 on all its boundary. And then we are also assuming, in a sense, that there are no bad essential singularities, so that also the behavior at infinity is good. If this is the case, basically, this is a bound. This is the bound of an analytic function that's bounded by 1. So by maximum modulus principle, if you move inside the complex plane, you still have to be bounded by 1, which means that this gamma 1 cannot be negative. Because if this gamma 1 is negative, then you would get a phase that grows with the positive coefficients. And this would violate the fact the function has to be bounded by 1. So this gamma 1 has to be positive. And this is analog to this to the positivity bounds that well, we all know. So, and of course, 1,4 is compatible with this condition. So the idea is essentially the same, is that knowing that the function is bounded all the way up to the uv by 1 on this boundary, and then go inside the complex plane. To do so, we define a new function that I will call S1. And this new function is made up of the S matrix. So it's just the S matrix, already in some complex point S. W is another point divided by Sz divided by S bar W divided by Z minus W, Z minus W bar. Now, this new function has nice properties. In the sense, this new function, if W is strictly in the upper half plane, does not have poles. And in particular, you can show that it's bounded by 1 on the boundary. So we can apply again the maximum modulus principle and expand this function, for example, when Z and W are close to the threshold. You can do it in any direction, so you can move in any direction, do this expansion. But in particular, if you expand along the imaginary axis, you get a very nice, very simple expression for this S1, which is just, so let me call X and Y the coordinates along the imaginary axis. In this function, it's just, well, if I don't take the modules, it's minus 1 plus 1 over 96 plus 8 gamma 3, xy plus dot dot dot. And this has to be greater or equal than minus 1. And this readily implies that this coefficient, sorry? No, minus 1. Well, in modulus to be bounded by 1.
Ah, sorry, the full thing.
Yeah, the full thing. Yeah, sorry. It's, so gamma 3 has to be greater or equal than minus 1 over 768.
How do you come up with this function? What is the
Right, right. Yeah, this is the what.
in any sense optimal or?
Yeah, in a sense, it's optimal. So there is a theorem in complex analysis. Actually, there is like a class of theorems called Schwarz-Pick and multi-point generalizations that basically, well, makes this statement that these kind of combinations in modulus are less or equal than 1. Another way to see it and another way that mathematicians say it is that when you have, well, this is a function from the upper half plane to the upper half plane, but can be a function from the disk to the disk. So mathematicians say that when you have an holomorphic function from disk to the disk, this is a contraction with respect to the hyperbolic metric. And actually, this expression, when you write it in the Poincaré disk, it looks like really the hyperbolic distance. So it's just a statement about analytic functions. So I don't know if someone can make sense of this, but it looks like related to some ideas to geometry. It's very nice. And and if you iterate this procedure, basically, what you do is that you start to scan higher and higher derivatives in this expansion, and you can bound these higher order coefficients, so gamma 5, gamma 7. You get a set of nonlinear inequalities. And let's see. I can show you a plot. Right. So this is how it looks like in this gamma 3, gamma 5, gamma 7 space, the region where these coefficients are basically allowed. Okay. So, well, there are some nice features. For example, maybe I can make a fast comment. Yeah. So, for example, there is a kink, and this kink corresponds to, it has some, it's like the S matrix found by Zamolodchikov for the flow from criticalizing to criticalizing, and then in principle we can determine analytically all the S matrices that lie on this boundary. But I won't comment further on this because, well, if you have questions, we can talk later. So let's switch to D equals 4. So in D equals 4, we cannot apply anymore these analytic tricks because of this, these functional relations. The crossing complicates these theorems, and we don't know how to write analytic expressions. But there is something that we can do. So now I'm talking about this full set of phase shifts. D equals 4, we have two Goldstone, so in principle we have a symmetric and asymmetric and singlet representation. And well, the only trick that, to get some analytic bounds, the only trick that I want to recall you is that the S matrix in the symmetric channel is bounded by 1, and it's the only one that is bounded by 1. So if I consider the S in the symmetric channel, it's bounded by 1 on all the real axes. And the fact that it's bounded by 1 on all the real axes, we can apply again this Schwarz-Pick trick and get some analytic bounds on this alpha 3 and beta 3. So on this alpha 3, for example, we get that has to be greater or equal than, again, this minus 1 over 768. But then there is some correction, phi square. And this is a very small number. This is over the like 3 times to 10 to the minus 5. It's a very small number. So this is the only thing that we can say analytically. So we run our numerics. And this is the allowed region for the alpha 3 and beta 3 parameter space. So the red line is the Schwarz-Pick bound. Is this bound that you can get analytically, and it's the only one. And it's nice that matches in 1 point at least. But then the full, non-perturbative completion of this bound is given by this curve that we don't know how to derive analytically. And well, this is the allowed region. There is some excluded region. And and what I will comment later is the pattern of resonances that you can get along this boundary, that we can measure numerically. So now let's use this bound on the alpha 3 beta 3 coefficients and this bound on the gamma 3 coefficients to draw some conclusions on the energy when you put the theory on a cylinder. So maybe I can cancel this now. And I'm not going to explain you all the, well, I'm not going to explain you the detail of this, but we basically use the effective Lagrangian. We do a perturbative expansion using, well, the operators that correspond to those deformations. And what we do is we get these corrections. And then we can read off a bound, plug in these analytic bounds. And the last thing that happens is that, for example, in D equals 3, the bound is of order 0.18. So these deviations to be less or equal than some positive number. And this is compatible with the fact that in D equals 3 dimensions, the GGRT formula can be exact. And this is a theorem by Sergei Victor and other people. In D equals 4, if we plug the analytic bounds that we found, this alpha 3, in this formula, instead what you get is that this bound is like negative. So the deviation has to be negative, which excludes 0. So it means that this GGR formula must be modified. And in principle, this bounds of this coefficient is something that one could, for example, measure on the lattice and compare with the deviation from this formula, for example. And let me mention another observable, for example, that one can study. So this is only about the ground state energy, but of course on the cylinder you have like all the other excitations. And in particular, in general, there will be a splitting between the 2 and 4 particle states. And again, this splitting between the state with excitations of momenta -2 and 2, with respect to the splitting of the energy level with 4 particles, basically, momenta 1, 1, -1, -1, is something proportional to gamma 3, and in principle, we are bounding also these coefficients. So this kind of observables that people can measure on the lattice and that we put bounds on it. Another check that let me mention of this, for example, of this bound is that you can compute the same energy splitting, not computing a perturbation theory with the Lagrangian, but with the TBA, for example, and they match. So that's a check that we did. And now, for the last part of the talk, let me comment a bit about the resonance pattern. So as I told you, our numerical procedure let us to go on this boundary and measure the S matrix.
Delta 4, maybe you said it. You have an upper bound on it, but has it been measured also?
No, actually no, because it's very difficult to get these deviations from the current lattice data, because it's really you should perform a fit in the 1/r expansion for very long strings and then read off these coefficients compared to the bound. That would be interesting, and in particular, it's compatible with the common law that the GGRT formula has to be modified in 4 dimensions, target space. So, right, so along this boundary, as I told you, we use our S matrix Bootstrap, and we can read off the S matrix for each point. This S matrix has resonances, and surprising for us, at least, is that for some region of this parameter beta 3, in particular for beta 3 positive, has some axion that has this excitation that has been predicted by Sergei, Victor, and other collaborators. And well, let me show you the patterns of this zero. So here what I'm doing is that I'm moving along this boundary of the allowed region. And for each point, I'm measuring, for example, the zeros in the antisymmetric channel. So in the S matrix that I get for the antisymmetric channel. And as you can see, for example, for this bottom plot, as I move, there is a zero, of course, even for beta 3 negative. But then, as we pass this point, that is interesting because it's the only point that satisfies Yang-Baxter, so it's the only integrable point. This resonance starts to get lighter, and the width, which is this gamma anti, that is basically the imaginary part of the zero, also gets smaller and smaller. And in particular, it was surprising for us that for some points along this boundary, the position of this zero basically coincides the one that has been fit for SU3 and SU5. And moreover, if we extract from this resonance the coupling to the worksheet Brannons, you can see that surprisingly also in this region matches basically the formula for the coupling that is derived for the theory to be integrable. So it's a coupling that basically has been predicted analytically and is a necessary condition for the d equals 4 theory to be integrable. And all the resonances that lie on this trajectory have basically this coupling. So also this is like a numerical observation that we don't actually have an explanation for that, but it's kind of tempting to see it. And then moreover, we have like our S matrix not only have this zero, but have other zeros, for example, that we call like with these names, let's say. But the feature is that they are all broader and they appear at high energies, so higher than the axion. So the axion is really the lighter resonance in this region. And if you want, I can show you a plot of how they look, these zeros in the disk as you move on this boundary instead of the S-plane, let's say. So this is the axion that I told you, this is the axion star, and then in the symmetric channel we see some other zero, and we see also like a zero in the singlet channel. But and the fact that these two patterns are symmetric is due to some symmetry of the crossing equation that I commented, but the antisymmetric channel and the singlet, they get exchanged as you move from one side to the other of this plot. It's just symmetry. So, well, this is all I wanted to tell you about the Bootstrap. So, well, some other directions that Joao also anticipated yesterday is, well, to look at these massless pions. And what is intriguing is that this same pattern seems to arise also when you consider massless pions. For example, that plot that Joao showed yesterday, if you rotate, it looks like a bit like this plot. And for example, on this side, even in higher dimensions, the resonance in the antisymmetric channel looks the most important at low energy. We still don't know about the other side, but there is this very nice parallel that we see with this, even in higher dimensions with this two-dimensional system. And then another direction that we are pursuing now is to add multiple particles. So to consider, for example, scattering of 6 Brannons, and see if imposing these additional conditions, it comes from the fact that the 3-to-3 scattering matrix has to be unitary, leads to stricter bounds on these low energy coefficients. And, well, I will stop here. Okay, thanks.
If I Kaya-Schwarzschild lemmas, am I supposed to sort of get analytic bounds that gradually get closer and closer to numerical bounds?
Yeah, you really need not really, in the sense that you really need because you see this analytic bounds comes only from the symmetric channel, but it seems that you really need to consider also the other channels, because there are more well, there will be not only like, you see in 3 dimensions you have only gamma 3 and then you have gamma 5 only. But in this in R dimension you have like more low energy constants.
There is no simple analytic way to improve on this.
Yeah, at least that we know. So the idea to do multiple scattering is that maybe considering also like 3 to 3, this region, for example, we start to get bounded for above. We exclude these very large values of the parameters of the low energy constants.
Any more questions?
I wasn't sure. I didn't quite understand this splitting between the E2 and E4. Can you say that? Is that, I mean, maybe just to clarify, you're imagining putting the theory in this cylinder.
Yeah.
Or the temporal extent is the infinitely large one?
Yeah, for example, the time is infinite large, the theory is on a cylinder. And then the splitting arises from the fact that this, so this formula, it's something that I didn't have time to comment fully, but this formula basically is compatible with an integrable description for this excitation. So if this formula is exact, then you expect that these energy levels are degenerate, basically. So the fact that there is a splitting is related to the fact that this formula gets corrected at this order. And that's why you get a...
What's the coefficient in front? How does it scale with R?
Well, the coefficients in front I can give it to you, but it's not particularly illuminating, it's just a number.
But it depends on R, right? It depends on R, 1 over R to some power.
Right. Sorry about that. It's like of order R to the 7. Same order as the, thanks.
If there are no more questions.
Okay, thanks.
Okay. Works now? Good. I sent the title, by the way, yesterday.
You did? Must be the organizers.
Title is due to Joao.
You should switch this on.
Oh, also this? Okay.
It's the camera that will follow you.
Oh. Ah, that's how it tracks.
Yeah, that's how. Okay, Victor will be our last speaker for here. No, not our last speaker, but the last one of the morning.
Okay, thanks. Yeah, so there were lots of expectations for my talk. In particular, something was supposed to become clear after it's, that we will see. So yeah, this is a sort of concluding talk about flux tubes, as all the previous 2 talks this morning. And I think that to be maximally entertaining, it's good to combine in your talk some pieces that are purely words, and some parts that are some calculations. Okay, so talk will consist of 3 parts. First will be some motivation and sort of, I would say, status of this theory, because it's a little bit stupid to give a review after the technical talks have been given. Then I will talk in details about one particular aspect of this flux tube theories, which is what we call soft theorems. And I hope I will have time to really show you some derivation, and I think it's a nice calculation that I hope you will enjoy. And then in the last part, I will sort of go back to some speculations. So this is, let's call it dreams. I will try to outline some future directions in the context of S-matrix bootstrap, and maybe sort of gear up for discussion session in the afternoon, as long as anybody other than myself is willing to discuss it after my talk. Okay, so let me start with motivation. Why am I so fixated on this flux tube theory? So there is a picture that appeared in Sergey's talk and Andrea's talk. We really shouldn't have erased it. We're thinking about some large N Young-Mills, say pure Young-Mills theory, and I will talk about 3 and 4 dimensions. Okay, there is Sergey's discussion focused mostly on 2. That's slight modifications that you need to do in 2 dimensions. And we consider really 2 probe heavy fundamental quarks and stretch a flux tube in between them. And for most of this talk, we take the length to infinity, in which case there is some 2-dimensional, what we call worldsheet theory. Okay? And okay, it just lives on flat Minkowski space, and that's why we can try to compute its S-matrix. Okay, good. So why is this object so interesting, to me at least? So this is something what we call long string, right? So the idea is that the sort of the grand program is that if we solve this long string, then we somehow hope to move to short strings. Short strings. And this, if these short strings are understood, that basically leads to string-like description of QCD. Okay, and this is some sort of dream of older generation. And then, okay, if this is done at n to infinity, then okay, one can try to proceed with 1 over n correction. And that would really be sort of understanding, at least from my point of view, confinement from first principles, because we have a theory that has a string-like description, so it by definition it confines, but in principle we can do reliable calculations to all orders. And well, we sort of know what historically happened 50 years ago when people tried to develop this idea. They actually developed the entire fundamental string theory, okay? So, well, I can also hope for some luck and develop something even bigger. But it's not a total joke, because well, usually after discovery of ADS CFT, we're told, well, now all the things are sort of came to peace because there's fundamental string theory, and then there is something like holographic QCD, okay, which basically describes again confinement in string theory description, and sort of everything is done. But so one of the points of this exploration of ours, so this is totally not, I mean, this is BS, okay? There is no holographic QCD. It's something that doesn't really make sense, okay? Instead, there is some string-like description of QCD that we're trying to develop, and of course it is some piece of this fundamental string theory, but from what we're learning, it's some sort of background of string theory that is qualitatively and completely different from the backgrounds that we know, that we have at hand. And the hope is that if we really understand this, this worldsheet theory very well, we may even learn something about some really conceptually new string theory backgrounds, okay? So why am I saying all this is that, at least for me, it's sort of important to have this big motivation, some big goals in mind, which of course were nowhere close to solving this theory first, but that's sort of the perspective, okay? Good, so having said that, let me go to the status of what we actually know about this theory, and this will be really in the form of some sort of bullet points. Okay, I don't really have time to to explain all of these things in the details, and moreover, some of them were already mentioned and explained in details in Andrea's talk and in Sergey's talk. Okay, so what do we know about this theory? So first of all, it's at some scale. There is some scale that I'm going to call lambda n, which goes like n to some power times lambda QCD. Importantly, it goes to infinity when n goes to infinity, at which the 2D theory is decoupled from the bulk. Okay, so in particular, in n to infinity limit, it becomes a unitary two-dimensional theory. Good. Second point is that low energy. And low energy means at energy smaller than lambda QCD. Also, I will use LS to the -1. Okay, the string tension to the -1, that is the same thing. So low energy description is understood as an effective field theory, okay? And the prescription here is the following, that this effective field theory, it has massless goldstones, xi, that go from, there are d-2 from 2 to d -1, for example. So there are d-2 Goldstone bosons that are massless, and low energy effective action should be constructed of sort of induced metric, if you like, on the worldsheet. That's given by 8 alpha beta plus d alpha xi, d beta xi. So all the covariance terms that you construct out of this metric, that will be allowed terms in the effective theory, and the leading term is the number Gotha action, which is just determinant of this metric. Okay, and then there are higher order terms, and we also understand how to introduce massive particles that are sort of non-universal but can also live on the worldsheet. And again, they couple covariantly to this metric. Okay, this is the prescription. Plus massive states that will become important at some point. So then the next statement is that S matrix exists. Okay. So there were lots of discussions yesterday when it exists. So in this theory, it definitely exists, and I mean it in the sense that there are no IR problems. Okay. So you may get worried about it, the massless particles, massless bosons in 2 dimensions. Okay, there are enough derivatives for each boson, so this thing exists. Okay, good. Next, local operators probably do not exist. Okay? Okay, this is a little bit of a more vague statement. The reason I bring it up, that again, Dennis, for example, gave a talk about extending Bootstrap with some inclusion of form factors of local operators. So in this theory, something potentially weird will be happening in this direction. Okay? Next thing, that S matrix, and that's something Sergey mentioned, and I will not be able to say much more. I'll just repeat what he said basically. It's as close, in some proper sense, to an integrable S matrix. So what do I mean? What do I personally mean by this? So in the IR, this statement is true because of symmetries. Okay? And this is the statement that classical number Gotha action is classically integrable, and that's also the infrared limit of these theories. So in the UV, we believe that something like this is true because of perturbative QCD in the UV. And that's what Sergey was saying, that it means that some hard scattering is integrable close to free, and then you dress it with some soft factor. And that's something that there is, I think, room for theoretical explanations to actually, for theoretical explorations to make this statement more meaningful, okay? And what's, I think one of Sergey's motivation to study this 2D theories is that 2D things are simpler, and maybe he can really make this precise in 2 dimensions, okay? So then this point that I'm going to talk about in details in the second part of my talk is that this S matrix satisfies soft theorems. And these soft theorems, they are of the following form, that this S, for example, 2 to n, in the limit when one momentum, one leg, some pi goes to 0, okay, it is some functional of S 2 to k, where k is smaller or equal than n. Okay, so this is something I'm going to talk about in some detail, so I will write down more or less what this functional is. But important point that these soft theorems are equivalent to all the symmetries of the theory. What I mean by that? We've also shown that if somebody constructed an S matrix that just satisfies this set of functional equation, then one is guaranteed that there is a theory which has all the symmetries of the flux tube theory that can have this S matrix. Okay, so this is sort of a necessary and sufficient condition to include all the symmetries of the theory. So that's why, I mean, these theorems are potentially powerful. Okay. There is lots of lattice data. So far I was just talking about basically Sergey's and my friend and myself and our collaborators' exploration of the theoretical part. So now there is lattice, which Sergey now also joined the community. But before Sergey, it was mostly Mike Tepper and Andrea Satanadorum. And on the lattice, there are two types of measurements on the lattice. There are long flux tubes where people sort of directly measure the spectrum of long flux tubes on the lattice, and glue balls, okay? And in principle, we can extract useful information from balls of this sort of most directly from long flux tubes because we study a long flux tube, but as Sergey showed, from spectrum of glue balls, we also learn a lot. And so first, it agrees with theory. Okay, so there is no sort of clash between lattice and theory, although it sort of used to be, I mean, it used to be in the past, but that got removed by changing the theory to the correct one. There are no extra massless degrees of freedom, okay? So this is something where lattice helps because theoretically you could say, okay, maybe by some coincidence or some principle that we're missing, there are extra massless degrees of freedom. So lattice shows that that's not the case. Okay, lattice also gives some information about massive degrees of freedom. Okay, so what I call resonances. And here the picture is the following. So in 4 dimensions, there is this 0 minus minus, it means a pseudoscalar particle that lives on the world sheet of 4-dimensional flux tubes, which has mass approximately something like, in string units, 1.4 plus corrections of order 1 over n squared. Okay, so maybe sometimes you see the number which is 1.8. In our talks, that's for SU3, but the n equal infinity value is something closer to 1.4. And the width is given by some interesting number, which is square root of d minus 25, okay, times some factor of 5, some numbers, plus minus, roughly speaking, 10%. Okay. With gamma over m is sort of small, so it's a relatively narrow resonance. In 3 dimensions, I will explain later why this square root of d minus 25, why I factored out the square root of d minus 25. In 3 dimensions, there are sort of no signs of any resonances up to energies that are okay. We can try to estimate what they are, but at least up to energies accessible in the lattice and in the global spectrum, there are no signs of resonances. Okay, what else did I want to say? I'll go over there. So as I already mentioned, at high energies, probably perturbative QCD should give us some hints, and well, there are even some hints from perturbative QCD already exist. Maybe I'll review that in the concluding part of my talk. Well, also I just wanted to mention something really briefly that, okay, we did not discover something big like string theory while doing this, but you might have heard that there was this sort of progress in understanding of some two-dimensional quantum field theory that goes under the name of TT-bar deformation. And sort of whatever Sergey's and I's and Guzman's modest contribution to this field, for us it was all some sort of corollary of thinking about flux tubes, because when you think about flux tubes, you're in some sense also think about two-dimensional gravity, two-dimensional quantum gravity, and that sort of helped us to make some progress in understanding this TT-bar deformations. Okay, so you get some purely theoretical outcome. Okay, so at this point, it should probably look to you that there is some infinitely long list of things that we know about these flux tubes. And okay, yeah, I think we know quite a bit. I mean, there is quite a bit of theoretical information that we have about this theory. It's not completely unknown to us. Is there any questions about any of these points? Maybe I should explain in some more detail. Well, okay, it's more about, I guess, I think, okay, so there are a couple of things. So Sergey had this paper where he noticed that there is some relation between QCD beta function that you, some numerical coincidence, if you like, between QCD beta function that you compute at high energies and the low energy coefficients in our 1pi effective action. So that sort of suggests that, okay, maybe there is some UV-IR connection. But maybe something more concrete is that if you try to count the number of states that you expect on the string, and if you just think of inserting, you know, some Polyakov loop to create it in terms of microscopic degrees of freedom, then in 3 dimensions, sort of what you can do to this flux tube, you can insert basically a plaquette that's orthogonal to it, okay, and that state becomes the goldstone. Well, in 4 dimensions, you have these 2 goldstones, but you can also insert a plaquette that's sort of, I mean, I cannot draw it, sort of perpendicular to the string, but in terms of insertion in your Polyakov line, you just insert Fij, basically, where I and j are transverse directions of the string. And that has the correct quantum numbers of our pseudoscalar state. So basically, one can hope that, okay, you really have UV perturbative description of the same degrees of freedom, and in the middle, so the point is that theory is where was I? Close to integrable. So in the IR theory is weakly coupled and we can compute. In the UV, we sort of also have some understanding of degrees of freedom and kind of arrive to the same results. Now in the middle, at scales of all the lambda QCD theories, of course, there is no small parameter, but that's the hope. That's why we're sort of hoping for Bootstrap. That's the part of the theory that you bootstrap, and then you sort of have everything. So that's kind of the hope. Okay. But this UV part is less developed than the AR, partially because we didn't really think much, and I don't know much about perturbative QCD. Other questions?
Can you compute something about this Fij?
Well, can I or can somebody?
Can somebody? So you pointed. So you're saying here that this thing indicates the existence of this resonance.
I guess so, yeah. That's much like I say. You see, the problem is that I know very little about, close to nothing about high energy QCD, and well, you know that high energy QCD is perturbative in a subtle sense, and one sort of first needs to identify which regime. Is it some SCAT, or is it some BFKL, or whatever the other regime? What are the techniques that you need to use? And I know very little. I think maybe for somebody with knowledge of this, he could give you a better answer. That's something we wanted to look at for some time, but never got to. Okay, I spent 20 minutes so far. Right?
Yeah.
Good. Okay, let me go to this soft theorems thing. So so this is something that basically you can find in this paper of 2014. Although we'd never really get there in the talks. At least I've given a talk. I mentioned the soft theorems in detail in my talk once. It was at CERN around the time when Slava Rычkov was still there. And after the talk, he told me that he was the only one in the audience who maybe understood something. So we'll see if since then anybody has reached Slava's level. So let me remind you some derivation.
That was very unfair to his colleagues.
Should I forget it was recorded? Pedro, can we cut? Okay. Look, I needed to gain the attention of the audience somehow. Take notes, Ricardo. So, okay, so let's start with something that so I'm going to use some sort of mixture of current algebra and effective field theory, okay? So one can pretend that he knows nothing about effective field theory and try to derive everything without Lagrangian, but that's not really the shortest, the cleanest point. So I will be using both my knowledge of Lagrangian at low energies and some sort of tricks from current algebra. So suppose I have some conserved current that will have a meaning of shift current, but we can start a little bit more generally. Alpha is the Lorentz index, and I is some label of the current that starts with something linear in my Goldstone field, okay? And plus something that I call, whatever it's called, little as alpha I, that doesn't have any overlap with one particle state, okay? Now let's insert this current in between some in and out states. Take the derivative and Fourier transform this object, okay? So now, and let's sort of study what this thing produces when I take my momenta to 0, okay? So naturally, there will be two pieces, the way I wrote it. There will be a piece that's when I insert something linear in the field, and there will be a piece when I insert the rest, okay? So from this, and okay, sorry, this is of course 0, because the current is conserved, okay? But let's rewrite this 0 in terms of two pieces, okay? So I have a piece which is just P alpha, okay, it's some out, sorry, usually let's put out here and in here, that's probably more conventional. So there is a piece where I just have my Goldstone field, okay? And there is a piece where I have P alpha acting on matrix element of my nonlinear in the fields component of the current, okay? And this is equal to 0. So now, let me not only take P to be small, let me also take P on shell, okay? Then what we get here, we basically have an LSZ formula for sort of an S matrix where I already pulled out all of my states into out and in, but there is one last state remaining, okay? So now if I take P on shell, so let me also take in both of this expression, I can take P, for example, equal to P plus, okay? My own shell is left and right mover. So let's take P be purely P plus. So here, and then I need to choose the sign of P0 to decide if my X goes into in or out state. But basically, for example, it goes into out state. So I have an extra particle, extra Goldstone added to the out state. And then I have in, which is an S matrix element of my out, P, and in, okay? And this is equal to P alpha times something, okay? And this together equals 0. So now, naively at least, we expect that when we take, because there are no more LSZ poles in this thing by construction, because the rest didn't have overlap with one particle states. So that's how we conclude that the S matrix element, which is, depends on in-out momenta that keeps hard, but in particular depend on P, is O of P, okay? So this is usual Adler's theorem.
It would be better to have an argument when you go to the split.
It would be better to have an argument.
When you don't do the split.
It's not a very standard argument, but this is exactly the argument that I will generalize in a minute, and you will see that split is important. Sure. Yeah, you could. I said that you could, but I think this will be the best to derive our result. Okay. Good. So this turns out to be true. Indeed, S matrix elements are single soft. But you will see that one needs to be careful, especially in 2 dimensions. We will see that one needs not only to look for LSZ poles, but one also needs to look for some infrared poles in concluding that some pieces go or not go to 0 when P goes to 0. Not really. Well, you will see. Not really, because of collinear singularities. Okay. So now we're going to use the fact that we have that our shift current in our theory is of a special form. How do we deduce that part? Well, in fact, our Lagrangian, as I said, did I erase it? Yes, sorry, I just erased it. Is a function of this metric 8 alpha beta plus d alpha xi d beta xi. So this shift current in particular, it shifts xi by some epsilon, okay? So now, because dependence of the Lagrangian is on this specific metric combination, I can show that my current actually has the following form. It's actually, because you see when I shift x by epsilon, metric, roughly speaking, shifts by derivative of x, okay? That's why shift current has the form of like translation by a derivative of x. So it looks like this, where this is a stress tensor, okay? Note that this stress tensor is a full stress tensor that has cosmological constant, so that's why this linear piece is indeed present here. Good, but because stress tensor is conserved, I can also write it like this, okay? So now, when I do my split, okay, I have a piece which is, I separate the piece linear in the field, plus I still have a total derivative of something that I will call, say, k beta alpha I, okay? Now look what we concluded. We concluded that this piece that was not supposed to produce any poles is actually a total derivative of something, okay? Which means that this formula can be rewritten in a following way. I mean, I'm just substituting this into this formula, really doing nothing. That's impossible. I just, for some reason. So you see, now, this is an S matrix element, okay? When P goes to 0 and P is in shell. Naively, it looks like it is of order P squared. And in higher dimensions, that indeed would be true. It's indeed true that the S matrix is doubly soft. However, in 2 dimensions, this is not true. In 2 dimensions, this object develops certain infrared singularities, but the claim that all of them are under control, okay? And I can really enumerate all of them. And there are only, okay, now let's focus, let's do, instead of doing something abstract, let's focus on some particular S2 to 4 S matrix element, okay? The claim is that if which means I insert 5 states in my out in. So the claim is that there is only 2 singular contributions to this expectation value of this operator that, roughly speaking, can be drawn in the following way. So there is. Okay, so yeah, let me draw the picture. And then I will explain. So there is this contribution. And there is this contribution, where I have this. This. Okay, so let me explain what I drew here. So I draw left movers going horizontally and right movers going vertically, because I cannot draw it by 45 degrees. And basically, what is drawn here, it is some, you see it is some, I have 5 external legs that have momenta K plus, P minus, Q minus, and P minus plus Q minus. And I insert my operator sort of over here. This is the insertion of operator, of this operator K, that I chose to be, so P is equal to P plus. It's a pure right mover. And this P plus is taken to 0 in this formula, okay? So the claim is that when this, you see what happens when this particle goes on shell, because those guys are both left movers, there is a 1 over P plus pole in this propagator, okay? It's sort of easy to see, I hope, right? Because I have P minus, Q minus, and this propagator is 1 over P plus times P minus plus Q minus, okay? So this is how I get 1 over P plus singularity. And this is an on-shell S matrix element with 4 legs, okay? And peculiarity of 2 dimensions that actually loops can also produce infrared singularities of the same strength as poles. And here I get the 6-particle on-shell S matrix element.
In higher dimensions, you get these only for specific.
Only for in some collinear singularities you'll get the same. But in 2 dimensions, collinear is generic. Yeah. Okay. Good. And then the claim, and then the insertion of this operator. What sees, so this cross is actually all what is left of this K that contributes to this kinematics is just X times D minus X, D minus X. Okay, so this is what's inserted here. Good. Okay, so now the point is that as we see, as I promised, in the limit, the soft limit of the S matrix element is bootstrapped by through itself, through the matrix element with 2 fewer legs and with a different matrix element with 6 legs. Okay, yes?
That there are no further relevant time singularities when you insert the
It's not obvious, but it's true, I think. I mean, if yeah, because there are enough derivatives. So if you try to insert more vertices, I mean, when you do this counting and you see that all of that does not, you always kill the pole.
D plus always appears up.
Yeah. The claim is that these are the only two diagrams with this minimal operator inserted here that have this 1 over p plus pole. Okay. Good. Okay. Let me, instead of this is a diagrammatic. Now you can write some integral equation that this thing satisfies. Instead, let me write just concrete formula in a somewhat simpler case. And the simpler case is that this, so you see this M6, this matrix element, it has both connected and disconnected pieces. And disconnected piece is always there. So now let's write a contribution where this M6 is fully disconnected, okay? And namely when M6 just factorizes as a product of basically two 4-particle matrix elements times some propagator, okay? So I want to replace this bulb by something like this, M4 and M4, and then I have the leg. So this is the contribution that is always there, and okay, I will sort of explain. I will explain what it is, and then you just get some expression like this. This S2 to 4 is equal to something linear in P plus times this. Okay, so times some object N3 of P minus and Q minus times. Okay. Plus some permutations, okay, plus something quadratic in this M4, okay, P minus P plus M4 of P minus K plus, okay, and here is 8 K plus P minus Q minus. And this N is some prefactor, some function of momenta, okay? So what's happening here? So M is an amplitude, S is an S matrix, and they're related in some simple way. And again, I just repeat that this is the contribution. If you want, there is also a contribution from a connected 3 to 3 S6 connected, okay? That I dropped. It's some integral that we can write out. So this is the conclusion, okay? So and then there is plus something of order p squared, okay? So the claim is the failure of double softness of the S matrix is uniquely fixed by lower order amplitudes. Okay? Good. So the last thing I want to say about this, so I just repeat that if your S matrix satisfies this, you can always write order by order in perturbation theory Lagrangian that is always satisfies all the symmetries. Okay, so it's a sufficient condition for realization of all your symmetries. And finally, sort of one of the results of this calculation is that. Oh, sorry. Yeah, thanks. I meant that. I mean, there are analogous formulas for all 2 to n. Yeah.
But at the end, given that, then there will be M6.
Yeah. You need. I just meant that it's really this soft theorem that fixes everything. I mean, this one is enough.
Is that will be because the singularity will be on the external things. Will be those finite part in this connected part in the 6 that
you just
will map.
Yes. Yeah. I mean, it's just you.
All in terms of
Yeah, it's all. I mean, you add external legs. 2 to 6, you just add it here and then here. But this piece is always sort of like this. Okay, just one last thing I want to say about this is that you can ask a question, okay, can I have S2 to 4 equal to 0 and this S6 connected equal to 0 to have the theory integrable? And the answer, well, it is some functional equation on your 2 to 2 amplitude then, and the only solution, so from this, the only solution is that S2 to 2 is equal to e to the IS. Okay, so that's how you prove that the only integrable S matrix consistent with the soft theorems is e to the is. Okay.
Usually soft theorems the way Weinberg does the value structure.
Yeah. Okay. Good. Okay, so let me in the remaining 5 minutes go to my unless there are other questions about this derivation.
But this is equals 3, or you're also doing
Okay, sorry, I missed. I started with an S matrix element when all the flavors are the same, and basically you don't get anything non-trivial if your flavors are different. So it happens in the sort of singlet flavor channel. Okay. Because you cannot put things on shell. If you start considering S matrix element with different flavors, you can never develop this Coleman-Thun singularity. You cannot put things on shell. Okay, so it's true in 3D and in 4D when I just took x1s on all external x, for example.
I already asked you this question, but I will ask you again. In 4D, we know that 2 to 2 at one loop is fixed, right? It's alpha 2 coefficient.
Yes. And this
should follow from symmetry.
Yeah.
But I don't know of any way of deriving it from this.
Yeah. And then, well, I can only give you the same answer that I also don't know. I mean, okay, Zhao's question is, we can phrase it in the following way. Can you say anything non-trivial about 4-point amplitude on its own? Is it related to some free propagator by analogous theory? And I do not know analogous statements. So I can relate 6 matrix element to 4 matrix element, but I cannot independently say anything about the 4-point S matrix element from these theorems. Okay, unless I require integrability, but I cannot fix it from these theorems. But what happens is that once you compute this one loop 2 to 2 S matrix element, you can show because it doesn't have in 4 dimensions, it does not comply with this form, you immediately conclude that you have particle production on the worldsheet and the theory is non-integral. And that's why I was saying that in 4 dimensions, the theory is non-integrable because of symmetries. One way to see it is because of the known one loop calculation and because of these equations. Okay, yeah. Let me say a few words.
The basic reason why you cannot start from the two-point function is that always the one you have in one function.
Yeah, and on shell 2-point function is 0. So yeah, I do not know what. Okay. Let me say a few words about what we think are the next steps, or what can we do further with this theory.
Stupid question, probably. But if you know that S2 to 4 is non-zero, then you know something. You have some bounds on M4, right? Because
Yeah.
you know it's inelastic. So.
Well, that's where I'm going. Yeah. Okay. Yeah. I mean that was one.
Something about 2 to 2. About M4 is what I want to.
Yeah. Well, let me say something, and then you ask again if that's what you wanted me to say, or if you wanted me to say something else. Okay. Yeah, okay. Just like 5 minutes. Not more. So let me summarize. So again, the program that we have, I just repeat that we first want to solve this n to infinity theory, and we have this conjecture with Sergey and friends that we call asymptotic axionic string ansatz, which is basically we're saying that the theory in D equal 3, Goldstone is the only state, and in D equal 4. We have Goldstone, 2 Goldstones, and the axion, and these are the only states. And now we know that the theory in D equal 4 is non-integrable. We also know from lattice data that in D equal 3 the theory is non-integrable. And well, we know something. We have a conjecture about the UV behavior. So we say that, for example, 2 to 2 S matrix. In the UV behaves like e to the is with some L UV squared, which is some sort of UV string tension. And from dispersion arguments, you can say that this L UV squared is smaller than the infrared tension, okay? Then there is some that I will call delta soft, some sort of factor that we emit that we emit into soft gluons, so that the 2 S matrix cannot be fully unitary. And then there is basically, well, in some sense, identity. Okay, some integral matrix which is trivial because the phase we believe it should be just to e to the is because of these arguments. Okay, so now maybe as we were saying, this thing as a function of s, maybe one can learn something about it from the UV, from the high energy QCD. So let me tell you what. So if this ansatz, suppose this is true. So what is the corresponding bootstrap problem that arises here? So I wanted to basically copy the formula from one of the talks a couple days ago, but I don't really have time to write it carefully. But I hope that you remember. Okay, so usually we or you parameterize the 2 S matrix as some CDD factor, okay? And here I factored out this our special e to the is part, okay, times what's called this Sx, which is a minimal solution, which basically takes care of the absolute value of inelasticity. It's some function that doesn't have any zeros in the physical sheet anymore, okay, and uniquely fixed by particle production. And basically, I think that most of the S-matrix bootstrap effort was focused on fixing this part, on fixing this SCDD. And what Sergey and I are saying that, well, we know this already, where we say that in d equal 3, this is just 1, and in d equal 4, it's just a single CDD factor with mass and width that we measured from the lattice, so we also know it. And the non-trivial part is to fix this, but it sounds like a different bootstrap problem, because if you impose not having zeros, so maybe have only 1 0 that you factored out, it is a different space of functions that you are bootstrapping. Moreover, as I understood Bolt's comment, if we put in some 2 inelastic S matrix into bootstrap, we can then substitute it into, well, sorry, if we learn how to include 6 particle S matrix elements in our bootstrap program, at least in some way, then there is a relation between 2 S matrix and 2 4 S matrix that just needs to be satisfied, okay, at every value of the moment. It's a particular limit of 2 4 S matrix. You take one of the particles to be soft, but okay, the rest of the particles can be arbitrarily hard, and that should be satisfied exactly. So this is an extra requirement, and in particular, again, you do not find the solution which has 0 2 4, just because the only solution is pure e to the s, and if you like, this will also be factored out. So the only S matrix is a pure identity that doesn't have 2 4. So in principle, this is some, at least it sounds like it's a physically well-defined mathematical problem. Okay, if there is any chance of solving it, that I do not know, but some hope or dream that Sergey and I have is that just to repeat myself, that in the infrared the theory is solved. In ultraviolet the theory is not solved, but this simplicity of global spectrum and this that as Sergey showed, it suggests that in the UV theory is also not so complicated. Okay, so maybe we have some handle on it in the UV. And there are some intermediate energies where, okay, there is no expansion parameter, and that's the hope, is that, okay, you at least fix it numerically, and okay, maybe it's, again, from lattice data, from global data, we see that numerically, there is no small parameter, there is no small parameter, but numerically particle production is small. So okay, if you have some numerical approximation that is good enough, okay, maybe you are close to, okay, what you can call solving your theory. Okay, it's not an integrable theory. You'll never write an expression analytic that solves it, but in any practical way, maybe we can solve it. Okay, let me stop here. I don't want to take too much extra time.
Comment because Victor didn't say like, this double softness, because Victor explained it the technical way, but it's really just non-linearized boosts. So this double softness is because the theory has not just shift symmetry, but also non-linearized boosts. But it's funny that in 1+1 dimensions, actually it doesn't hold singularities. That's the price to pay for having those softness.
Yeah, maybe I think I forgot to say. I forgot to say because somehow in the derivation that we have, we never use this. I mean, we don't explicitly use this fact. Yeah, so, I mean, yeah. Exactly, yeah.
Examples of the fact that Lorentz invariance of the dimension has different consequences.
Yeah, this is nonlinear Lorentz invariance.
Yeah.
This is d-dimensional Lorentz invariance. Yeah, just to clarify the logic a little bit. I mean, I was a little bit rushing. The fact that, I mean, indirectly I said, the fact that Lagrangian is a function of this object is in one-to-one correspondence to having nonlinear Lorentz invariance. Okay, and then I actually use this technical fact to derive my soft theorems.
Coming back to my question, so I thought you were saying that all the consequences of this nonlinear realized symmetry are this soft relation with soft theorem.
Yes. Well, there are, so you see, so yeah, so careful step is the following. So you need to compute 3-level and 1-loop 2-to-2. That's the careful statement. Then require all the analytic properties of the S matrix and these theorems. Okay? It's true that there are other properties that the S matrix satisfies. For example, you can take 2 legs soft and there will be some commutator, you know, the story. But the claim is that this somehow will follow in some way. Like if you construct the S matrix that satisfies this, it will automatically satisfy that. That's the theorem. Doesn't mean that those things are useless. I'm just saying that this is a complete set of requirements. Like if you construct the S matrix with these properties, you're guaranteed that you solve the physical problem.
Okay, if there are no more questions, then let's thank Victor again. Oh, if you want dinner, then